Previous session we discussed about the what are the concept of theory of simple bending. In this session we will solve the problems related to the theory of simple bending, and also we will discuss few of the features of shear stress distribution in the beam. And also one of the important point while solving the problems, these are the 4 standard cases you should know. That is, one is a simply supported beam with a central point load for which maximum bending moment is WL by 4. That is, we are using if it is a problem is given with the central point load. If it is an uniformly distributed load, simply supported beam carrying an uniformly distributed load throughout its span, for calculating the maximum bending moment. For calculating maximum bending moment, we are using WL square by 8, and then if it is a cantilever beam carrying a point load, maximum bending moment will be W into L. If it is a cantilever beam carrying an uniformly distributed load throughout its length, its value is WL square by 2. These are the 4 standard cases which we discussed in the bending moment and shear force diagram unit. Same we are using here for calculation of maximum bending moment. Let us take an example number 3. Previous session I solved 2 problems in which we have determined the load. This is the problem number 3, where the rectangular beam is a rectangular beam, simply supported, case is simply supported, and its span is 4 meter, carrying an uniformly distributed load of 50 kilonewton per meter. That is the simply supported beam carrying an uniformly distributed load throughout its span. Find the dimensions of the beam. In this problem, we have to find out the size of the beam. Here one dimension is relation between the 2 dimensions is given, 2.5 times its width, depth is 2.5 times width. Take maximum bending stress in the beam section as a 60 MPa. This is F is given, F or sigma, bending stress we can abbreviate as in sigma or F. This is 60 MPa, that is 60 newtons per mm square. These are the data given. We have to list out the data first. Span is given 4 meter, W is that is load 50 kilonewton per meter, D is depth is 2.5 times the width, and stress is that is bending stress is 60 newtons per mm square. What we have to find out? We have to find out the size. To find out the size, what are the formulas we required? First we have to list it out. First if we have the load, we can calculate the moment. M is equal to WL square by 8. That is for the simply supported beam carrying in UDL throughout its span. By using the WL square by 8, we can calculate the maximum bending moment. That M can be equal to the M is equal to ZF. Moment of resistance is equal to ZF. Let us see. First maximum bending moment. Maximum bending moment is WL square by 8. W is 50 kilonewton given, W is known and L is also known. 50 into 4 square divided by 8, that is 100 kilonewton meter. We have the value in the kilonewton meter because we use the values of W as its kilonewton per meter and L as a meter. That is why answer is 100 kilonewton meter. That we have to convert into the 10 to the power of 6. 100 into 10 to the power of 6 Newton mm. Convert the kilonewton meter into the Newton mm. Why? Because further we are using the bending stress as in 60 newtons per mm square, which is the unit of Newton per mm square. Instead of converting the 60 newtons per mm square to the meter per meter, the kilonewton per meter square or Newton per meter square, it is easy to convert the bending moment into the Newton mm. Next we can equate this bending moment to the Z into F. That is, moment of resistance is given by the Z into F, where Z is the section modulus, F is the bending stress, which is given 60 newtons per mm square. If we know the F value as well as we know the M value, that is M value, we are equating the moment of resistance is equal to maximum bending moment. If we know these two unknowns, then Z can be Z is the only one unknown that we can find out. Section modulus is given by, for a rectangular beam, Z is given by 1/6 BD square. 1/6 BD square for rectangular section. That is, we are equating the M is equal to, M is 1.66 into 10 to the power of 6, and Z is, this portion is Z, okay, into F. If we equate, and then B cube is equal to 1.66 into 10 to the power of 6 by 1.04. Therefore, B cube root of 1.59 into 10 to the power of 6, that is equal to 116.71 mm. D will be equal to 2.5 times B, which is given in the problem. 2.5 into 2.5, that is equal to 291.79 mm. B is 116.7, and then this is D is 291.79 mm. Like this, we have to equate the bending moment with the, we have to equate the M is equal to ZF, M as in bending moment, and Z value 1/6 BD square, and then multiply with F, we will get the, on simplification, we will get the D and B value. Let us take a second problem, next fourth problem. A cast iron test beam 20 mm into 20 mm. Cross sectional details of beam is given 20 mm into 20 mm and 1 meter long and supported at its ends. It is a simply supported 1 meter length, and it carries a central load. It is a W point load. It is not UDL. Point load 640 Newton. 640 Newton, if you convert to kilonewton, it is 0.64 kilonewton. What UDL, what uniformly distributed load will break the cantilever? If in this case, first case is given as an simply supported beam carrying a central point load. By having in this simply supported condition, we have to find out the stress value. See, first case is cast iron beam simply supported. Given is breadth of the beam is 20 mm, depth of the beam is 20 mm, and span is 1 meter. W is 0.64 kilonewton. For simply supported beam carrying a central point load, maximum bending moment is WL by 4. Maximum bending moment is WL by 4. Therefore, maximum bending moment 0.64 W is given, and L is 1 meter divided by 4. That will be 0.16 kilonewton meter. If you convert this into the Newton mm into 10 to the power of 6, you will get a 0.16 into 10 to the power of 6 Newton mm. Now we have the moment value, and then we will calculate the Z value. Z is equal to 1/6 BD square for the rectangular section, rectangular or square. Now 20 into 20 square, that will be 133.36. Now we have the maximum bending moment and Z value. M moment of resistance is equal to maximum bending moment. Therefore, M is equal to Z into F. By having a relation M is equal to Z into F, we can find the bending stress in the beam. Moment of resistance M is equal to ZF. Therefore, F is equal to M by Z. We know the M value and we know the Z value. By substitution, we will get the stress as in 120 newtons per mm square. Now we have the value of F. Second case in the problem is given. If it is an same beam, same material, beam is made out of same material. If it is used as an width is equal to 50 mm and depth is equal to 100 mm, and as in cantilever beam of span 2 meter, what is the load? We have to find out the load, uniformly distributed load. Now for given given section, find out the Z value. Z is equal to BD square by 6. B value and D value is given. Therefore, 50 into 100 square, that you will get 8333.33 mm cube. Then moment of resistance is equal to Z into F. We have the Z value, and then F is determined from first case. We have got the 120 newtons per mm square, and here Z value if you multiply this, you will get 10 into 10 to the power of 6 Newton mm as a moment of resistance. Now moment of resistance is equal to maximum bending moment. For maximum bending moment for simply this cantilever beam carrying an uniformly distributed load is WL square by 2. WL square by 2 is the maximum bending moment for cantilever beam carrying an uniformly distributed load. Substitute the value of M as in 10 kilonewton meter, M value you know 10 kilonewton meter, and W we have to find out. L value 2 meter is given in the problem. Therefore, W is equal to 2M by L square. If you cross multiply, you will get the M value, W value as a 5 kilonewton per meter. This is the, we can see again problem what is given. A cast iron test beam 20 mm into 20 mm in section and 1 meter long and simply supported at its ends fails when the central load of 640 applied. What uniformly distributed load will break the cantilever beam of same material? Material is same, that is why we have taken this stress 120 newtons per mm square for both cases. We have taken same value. First case we have got the 120 newtons per mm square stress, that is substituted in the second case, and then he is given the 50 mm side, 100 mm width and 2 meter long. $120 we have the value, that 120 is substituted here. In this case 120 newtons per mm square, whatever the F value we have, that is we are substituted in this case, and then determine the M. From the M we got the W. Now next let us consider one more problem in which timber beam of rectangular section 100 mm wide and 200 mm deep, size of the beam is 100 into 200, carrying an UDL, it carries an UDL of 8 kilonewton per meter. Find the span. We have to find the span, and bending stress is given as an 10 newtons per mm square. Let us write down the data given. B is 100 mm and then depth is 200 mm. W 8 kilonewton per meter. Stress is, bending stress is 10 newtons per mm square. These are the 4 values given. We have to find the span. If you want to determine the span, where is the, in which formula it will be there? M is equal to WL square by 8, because it is a simply supported beam carrying an UDL throughout its span. M is equal to WL square by 8. WL square by 8 means M we should know. To find out the M, we have to use the formula M is equal to Z into F. Z can be determined by having an B and D. 1/6 BD square, if you use formula, we will get the Z value. M is equal to Z into F. Z into F, it is already given in the problem, therefore M we will get. Then after getting the M, M is equal to WL square by 8 for simply supported beam, from where we can get the L, span. Like that, before solving the problem, you should analyze, and then which formula is suitable for particular problem you have to determine, then substitute. First find out the Z. Z is equal to 1/6 BD square. B is 100 mm given, B known, and D also given in the problem. Therefore 1/6 100 into 200 square, which is 6.66 into 10 to the power 5 mm cube. Second step is M is equal to ZF. Moment of resistance is equal to Z into F. Z is 6.66 into 10 to the power 5 into ZF 10. It is given in the problem. F is bending stress as a 10. Therefore, M is equal to 6.66 into 10 to the power of 6 Newton mm. That Newton mm you have to convert into the kilonewton meter, because further we are determining the span in the form of a meter, and also we are substituting W value as a kilonewton per meter. W value we are not converting into Newton per mm, we are substituting directly as a kilonewton per meter. That is why you have to convert the m value into kilonewton meter. Now m is equal to WL square by 8 for the simply supported beam carrying an uniformly distributed load. Therefore, m value is 6.66 here determined, and then L we don't know, and W is 8, which is given in the problem. Therefore, L square is equal to 6.6, then L is equal to square root of 6.6. You will get L value as a 2.58. Span of the beam is 2.58. In next problem, here moment of inertia of a beam section 500 mm deep is 6949 into 10 to the power of 5 mm to the power of 4 is given. Why it is given like this? In this problem, size of the beam is not given. Instead of size of the beam, only depth is given and moment of inertia is given. Moment of inertia of a beam section is 500 mm deep. 6949 into 10 to the power of 5 mm to the power of 4 is the moment of inertia. Find the longest span. In this problem also we have to find out the span over which the beam of this section when simply supported could carry UDL of 50 kilonewton per meter. Load is given and also then size of the beam is not given, only depth is given and moment of inertia is given, from which we have to find out the span. The maximum bending stress in the material not exceed the 110. Bending stress also given in this problem. And second case, if the UDL is replaced by point load, instead of UDL 50 kilonewton per meter, if it is replaced with point load of W, what is the value of load? That is second case. That we will consider afterwards. Let us solve first, determining the longest span. What are the data given? D is given 500 mm, and moment of inertia is given, that is 6949 into 10 to the power 5, and then UDL is given 50 kilonewton per meter. Bending stress is given, which is 110 newtons per m square. These are the 4 parameters given. To find out the Z is equal to 1/6 BD square. But here we cannot use the 1/6 BD square. B is not given, only D is given. Another definition for Z, common definition is Z is equal to I by Y. I is there, Y is the maximum distance from the neutral axis. That is, maximum distance for rectangular section is D by 2. Here D is 500 mm, therefore Y will be 500 divided by 2, that is 250. I divided by Y, if you calculate, you can get easily Z value as a I by Y, that is of 6949 into 10 to the power 5 divided by 250. After knowing the Z, M is equal to ZF. Z you know, F already given in the problem, M you can find out. Then having in relation for maximum bending moment, M is equal to WL square by 8. You have to equate the moment of resistance with the maximum bending moment, then you will get the longest span. Okay, let us see here, section modulus Z is I by Y maximum. I is T by 2, that is 500 divided by 2, 250 mm. Z is equal to 6949 into 10 to the power of 5 divided by the 250. We have used the relationship Z is equal to I by Y. You can see here 27.79 into 10 to the power of 5 mm cube is the Z value. That is why when looking the problem, carefully note down the data given with its notations, and then you can list out the what are the formula you know. Z, we have the two types of formula. One is Z is equal to I by Y, common formula for rectangular section. Z is equal to 1/6 BD square. Whether which formula is suitable for section modulus, that you have to analyze. Once you get the Z, if F is always given, then Z into F you will get the M value. Now we have the relationship M is equal to WL square by 8 is the maximum bending moment formula for simply supported beam carrying an uniformly distributed load. L square is equal to, if you cross multiply, 8 into M divided by W will be L square. Therefore, L square is equal to 8 into M divided by W. 8 into M value, what is the value of M? M value is 305.75, because 305.75 into 10 to the power of 6 Newton mm. We substituted all the values in the mm. That is why here it is the, we are substituted as a mm. That is why we got the value as a Newton mm, that we have to convert into the kilonewton meter. If you remove 10 to the power of 6, you will get the value as a kilonewton meter. M is equal to WL square by 8. L square is equal to, this is the value 48.92. Therefore, span is 7 meter. Next, in this problem, if it is replaced with the UDL is replaced by the concentrated load. If it is UDL is replaced with the concentrated load, what is the value of W? If it is a concentrated load, maximum bending moment will be M is equal to WL by 4. Now we have the value of L. Okay, M it is there and L we know. To find out the W, cross multiply 4 into M divided by L. L is 7 meter, L known, and M is 305.75 kilonewton meter. 4 into 305.75 divided by 7, that you will get 174.71 kilonewton as a W value. In this problem, again we can see the problem what is given. First case is simply supported beam, and then if the UDL is replaced by the W for the above beam, what will be the maximum value of above beam? Means again we can use the values of first case, that is a bending moment we can use here, and from which we can find out the W value. That is for W value is 174.71 kilonewton. Next problem here, a timber joist 150 into 250 mm, size of the beam is given as in 150 into 250 mm, is simply supported over a span of 3 meter. Span is given 3 meter, L is given, and size of the beam is given 150 mm into 250 mm. Breadth of the beam is 150 and depth of the beam is 250. It carries in total UDL of 10 kilonewton per meter inclusive of its own weight. Find the maximum stress induced in the joist. We have to find out the stress in the beam. Maximum stress means F or sigma. B is given 150 mm, D is given 250 mm, span is 3 meter, W is 10 kilonewton per meter. Since size of the beam is given, B and D is there, B 150 mm, D is 250 mm. For rectangular section modulus for rectangular section is 1/6 BD square, B 150, D 250 square. If you simplify, you will get 1.56 into 10 to the power of 6 mm cube as a Z value. Once you get the Z value, moment of resistance is equal to Z into F. Z is 1.56 into 10 to the power of 6 calculated, and we need the F value. F is question mark. Okay, to find out F, what we have to do? We have to equate the maximum bending moment is equal to moment of resistance. Maximum bending moment WL square by 8. What is the span given in the problem? Span is 3 meter and W is 10 kilonewton per meter. It is a uniformly distributed load. WL square by 8. WL square by 8 is maximum bending moment for simply supported beam carrying an uniformly distributed load throughout its length. Therefore, 10 into 10 to the 3 square, span is 3 meter divided by 8. Therefore, 11.25 kilonewton meter is the maximum bending moment. 11.25 into 10 to the power of 6, we have to convert this kilonewton meter into the Newton mm. Why we are converting? Because we need the answer F in the Newton per mm square, one important point. And also here Z value 1.56 into 10 to the power of 6, it is in the mm cube. Converting the mm cube into the meter cube is difficult. Instead of that one, it is better to convert the Newton mm kilonewton meter into the Newton mm. Here this Z value is m is equal to Z into F. Z value is in mm cube and 11.25 into 10 to the power of 6 is in Newton mm. Therefore, answer you will get as an Newton per mm square. Therefore, F is equal to, if you cross multiply, you will get 11.25 into 10 to the power of 6 divided by 1.56 into 10 to the power of 6, that is 7.21 newtons per m square is the stress. Next, let us see one more simple problem, but in which in this case question is sketch the variation of bending stress in the beam across the beam. We have to find out the bending stress distribution. In previous session I have shown the how bending stress is distributed in the rectangular beam. That is what is the value that we will determine in this problem. A simply supported beam, span is 6 meter, span is given as in 6 meter, subjected to an uniformly distributed load of 15 kilonewton per meter. It is a case of simply supported beam carrying an UDL throughout its span. When a simply supported beam is carries an UDL throughout its span, maximum bending moment will be WL square by 8. Let us see here 15 kilonewton per meter over entire span. The cross section of the beam is 200 mm wide and 300 mm deep. Size of the beam is given 200 mm as a wide and 300 mm deep. Sketch the variation of the bending stress in the beam cross section. We have to find the value of a bending stress at the two ends and sketch the bending stress distribution. Now first this is the problem given, span is 6 meter, load is span 6 meter and then UDL is 15 kilonewton per meter. This is the UDL value, and then size of the beam is given 200 mm wide, breadth is equal to 200 mm wide and depth 300 mm deep, depth is given, these are the details given, okay, and the load is given, load is 15 kilonewton meter. First find out the section modulus. Section modulus Z is equal to 1/6 BD square. Since B and D is given, B and D is there, by having a value of B and D, find out the Z, 1/6 BD square. B is 200 mm, D is 300 mm given in the problem. Therefore, Z is equal to 300 into 10 to the power of 4 mm cube. We have the value of Z, then maximum bending moment, because it is a simply supported beam carrying an UDL 15 kilonewton per meter throughout its span. Maximum bending moment is given by M is equal to WL square by 8. WL square by 8. W value is 15 and L is 6 given, divided by 8. That you will get as in 67.5 kilonewton meter. You convert this kilonewton meter into the 10 to the power Newton mm by multiplying with 10 to the power of 6. 67.5 into 10 to the power of 6 is the maximum bending moment. For bending stress, we have the equation M is equal to Z into sigma, ZF or Z sigma. Therefore, sigma is equal to M by Z. M is 67.5 into 10 to the power of 6 and Z is 300 into 10 to the power of Z value 300 into 10 to the power of 4. If you substitute M value as well as Z value, you will get the sigma value as a 22.5 newtons per mm square. And this is the beam is a rectangular beam. What we discussed in the previous session, this rectangular beam bending stress distribution will be maximum at the top both extreme edges, and at the neutral axis it is 0. Neutral axis lies exactly at the center, that is d by 2 distance. Then also this upper edge is the compression stress. If it is a simply supported beam, top fibers will be undergo the compressive stress and bottom fibers will be undergo the tensile stress. For this condition, we have to draw the bending stress distribution. Let us see how bending stress distribution. First, you draw the size of the beam, 300 mm depth and 200 mm width, and locate the centroid. This centroid will be at a distance of this centroid distance will be d by 2. It is a rectangular section, that is why it passes exactly at the central of the d, that is d by 2. This is the neutral axis. Okay, we have the value of a sigma. Value of sigma, that is bending stress, is 22 newtons per mm square. Here in this, first draw the vertical line and then mark right of it 22.5 newtons per mm square as a sigma c. Here you observe here sigma c, sigma t. This is sigma c is compressive stress, sigma t is a tensile stress. Draw a vertical line and then mark 22.5 newtons per mm square right side, and then bottom extreme edge draw 22.5 newtons per mm square left side. Join these two lines, you will get the bending stress distribution. What we can observe here, this bending stress is 0 at the neutral axis, and it changes to tension to compression. It keeps on increasing, slowly it increases. It is maximum at the extreme fiber. At the extreme fiber it is maximum, and at neutral axis it is 0. This diagram shows the variation of bending stress from the neutral axis to the extreme edge. Both the values are same because it is a rectangular section. Let us take one more example. Sketch the bending stress distribution across the cross section of the rectangular beam 230 into 400 mm subjected to 60 kilonewton meter. In this problem, moment is given. In previous problem, moment is not given. You can observe what is the difference between the previous problem and this problem. Here, he has given the load and the span. From the load, span and load, we have determined the moment as a WL square by 8. By using the formula for maximum bending moment, we have determined the moment. This value is already given in this problem. In this problem, moment is already given 60 kilonewton meter. Data given is M is 60 kilonewton meter, B as a 230 mm, D as a 400 mm. Now we have the formula Z is equal to 1/6 BD square for the rectangular section. By using this formula, B is equal to 230 mm, D is equal to 400 square, therefore 613.33 into 10 to the power of 4 is the Z value, section modulus for this given section. Once you know the Z value, calculate sigma. Sigma is equal to M is by Z, or M is equal to Z into sigma, from which using this relationship M it is given 60 kilonewton meter is given, that we are converting into the Newton mm, divided by Z value is 613.33 into 10 to the power of 4, from which we will get the value of 9.78 newtons per mm square as a sigma value. Once you have the bending stress, drawing bending stress distribution is very easy. Just draw the cross sectional details of the beam and then draw vertical line, and then right side 9.78, left side 9.78, proportionate scale, draw according to proportionate scale, then join this, you will get the stress distribution in the beam. Now next problem here, simply supported beam 4 meter long, span is 4 meter, and it carries in 3 kilonewton at the mid span. It is carrying a central point load, and the beam rectangular 100 mm side and 300 mm, this cross section of the beam is rectangle, 100 mm side and 300 mm depth. Okay, this is the details is given. Span is 4 meter, load is 3 kilonewton, width is 100 mm, depth is 300 mm. Maximum bending moment for simply supported beam carrying in central point load is WL by 4, from which we will get the moment as a 3 into 10 to the power of 6 Newton mm after conversion. Therefore, section modulus Z is equal to 1/6 BD square, B and D is given, therefore Z is equal to 150 into 10 to the power of 4. Sigma max, maximum bending stress is asking, that is why sigma max is equal to M max by maximum bending moment divided by the Z, 3 into 10 to the power of 6 divided by 150 into 10 to the power of 4. That you will get an sigma max as a 2 newtons per mm square. This is the one problem I have taken related to T section. For T section, what is the maximum tensile and maximum compressive stresses? We know T section, this neutral axis will not remain at the center. We have to find out the position of the neutral axis. After knowing the position of neutral axis, we can find out the stresses. This is the T section is given. 100 mm is the top length size is 100 into 20, and then 80 into 20 is the web portion. This is 80 into 20. We have to locate this neutral axis position. This neutral axis position we have to locate how we did in the geometrical property for determining the centroid. We have to find out the centroid. We will calculate the y bar value. Like that, here we have to determine the y bar, that is 67.77 calculated from the location of neutral axis from the bottom, or from top it is a 32.23. Total is 100. If you know the 67.77 as in value, if you minus from the 100 minus 67.77, you will get the value of 32.23 as a position of neutral axis from the top edge. You have to locate the position of neutral axis for calculating the maximum compressive and maximum tensile stress. To locate the position of the neutral axis, y bar is equal to a1 y1 plus a2 y2 divided by a1 plus a2. We have to find out the a1, a2 and y1, y2 for this figure. We have the figure 1 and figure 2 rectangles, a1 100 into 20 and a2 into 20. a1 a2 we have to find out. a1 is 100 into 20 and a2 is 80 into 20, and then y1 20 divided by 2, center of this figure 20 divided by 2. Then for center of second figure from the top edge, it is 20 plus 80 divided by 2, or if it is calculated from the bottom, you have to calculate from the bottom, then 80 divided by 2 this y2, and y1 will be 80 plus 20 divided by 2. Like that, 80 plus 20 divided by 2 from the bottom we are measuring. 80 bottom, first figure center is 80, depth of the flange, depth of the web, plus 20 divided by 2 is the center of that rectangle, first rectangle, and then 80 into 20 is the second figure area, and then its center is 80 divided by 2. By using this formula, you have to locate the center, that is 67.77 mm is from the bottom. Neutral axis lies at a distance of 67.77 from the bottom face. From the top face, it is 100 minus 67.77, that is 32.23 is the value from the top. Therefore, we can have two values, y1 value and y2 value. y1 is 32.23, y2 is the 67.77. And then we should know I value also. For calculating the I value, for two figures, I1 is the first top flange about the neutral axis. Moment of inertia of the top flange about the neutral axis is given by the moment of inertia of the rectangular portion plus A into distance of the CG from the neutral axis. That 100 into BD cube by 12 for the first figure. First figure breadth is 100 and depth is 20. 100 into 20 cube by 12 plus area of that figure, that is 100 into 20 into distance from the neutral axis, that is 67.77 minus 90. That you will get the value of I1 as 105 into 10 to the power 4 newtons per mm square. Similarly, we have to determine the I2, second figure, moment of inertia of the web about neutral axis, moment of inertia of the web about its CG plus A2 into distance of CG from the neutral axis, that is 20 into 80 cube. Web portion is size is 20 into depth is 80 cube, 20 into 80 cube divided by 12 plus 80 into 20, that is area of the web portion, into distance from the neutral axis. CG is the distance of CG from the neutral axis, 67.7 into 40, 67.7 minus 40 whole square, that you will get 208 into 10 to the power 4. That is you have to use the skill of geometrical properties chapter, where we have determined the moment of inertia of T section. By having the value of I2, add I1 and I2, you will get 313 into 10 to the power 4 Newton mm to the power of 4 as a I value. Once you have the I values, find out the m WL square by 8. It is given in the problem. W value is given, W is given and span is given. Now, to find out the stress, m by I into y1. Which formula we are using? M by I is equal to F by y, that is sigma y. Bending equation is sigma y is equal to m by I into y1, that is m we know 12 into 10 to the power 6, and then I value 313 into 10 to the power 4 into y1 value, y1 y2 we are separated. Starting we are determine the y1 y2. y1 is 32.23 and y2 is 67.71. and also I value is 313 into 10 to the power of 4 mm to the power of 4. Y1, substitute Y1 value here 32.23, you will get the sigma C as a compressive stress as in 123.56 Newton per mm square. Then Y2 value 67.77, again same formula, sigma T is equal to m by I into Y2 value. Y2 is 67.77, you will get 259.82 as a maximum stress. Like this we have to determine the maximum stresses. Next this is the last topic in this unit, shear stress in the beams. We discussed the bending stress in the beam. Now let us see how shear stress distribution in the beam. When beam is pure bending, the only what we observed when beam is under the pure bending, the only stress resultants are bending moments and only stresses are normal stresses. We have seen when beam is subjected to pure bending, only bending stress is considered. Most of the beam is subjected to the both bending moment and shear force. We observed in previous unit, beam is subjected to the bending moment as well as shear force. We cannot get the pure bending condition. Then definitely when shear force is there, then normal as well as the shear stress also developed in the beam. The normal stresses are calculated from the flexural formula. What we did problems by having in flexural formula, we can find out the normal stresses. Shear force F is distributed in the form of a shear stresses tau. We are using the abbreviation as in tau, acting tangentially to the cross section of the beam. The shear stress will be acts at the tangential to the cross section of beam. And also we observed bending stress is not uniform. It varies from the neutral axis to the extreme edge. It varies linearly. The bending stress varies linearly. Similarly, the shear stress due to shear force is not uniform and varies, making a parabolic curve. Bending stress varies linearly, whereas shear stress is not uniform and it makes the parabolic curve. And shear stress is usually maximum at the neutral axis. See, here it is the reverse case. What we observe, bending stress is 0 at the neutral axis and maximum at the extreme edge, whereas here shear stress is usually maximum at the neutral axis, and always if the thickness and also it is when it is a thickness is constant, or if the thickness at the neutral axis is minimum for the cross section such as I beam and T beam. But 0 at the top and bottom of the cross section as normal to the shear stress is maximum minimum. What we observe, bending stress is maximum at the extreme edge. Here shear stress is 0 at the top and bottom. For this type of, and one more important point is the shear stress developed is of small magnitude. If we observe shear stress values, it is very small magnitude. It is not large as the bending stress due to the bending moment. But for an academic interest, we should know how shear stress varies in the beam. The shear stress at any point, shear stress at any point of the cross section is given by the tau is equal to FAY bar divided by I into B, where F is the shear force, A is the area of the cross sectional area of the beam, Y bar is the cross sectional area of the cut section where we are determining, and then Y bar is the centroidal distance from the area A which is we are considering. This is the formula for determining the shear stress, and it is abbreviated with the tau. Let us see how shear stress distribution occurs in the three cases. First is rectangular section, second one is T section, third one is I section. These three sections we will see how shear stress distribution occurs. One is rectangular section. This is the cross section of the beam, and you can observe here shear stress is 0 at the two ends, and it increases at the neutral axis, and again it is reduces at the air, and somewhere here it is the average shear stress and maximum shear stress at the neutral axis. Okay, and it is a parabolic curve. Shear stress distribution is parabolic. This is the for the rectangular section. Next, let us see in I section. You can observe here shear stress is maximum, and at this flange it is small, and shear stress at the junction of flange and web. This junction of flange and web suddenly abruptly it increases to here also you can observe here junction it is increases, and it is a parabolic. It is a parabolic, and it is maximum at the neutral axis. Okay, at near the flange it is less, and somewhere it is this is the maximum shear stress. Okay, somewhere it will be here it is the stress at the near the junction, and this portion is the flange portion, flange shear stress. This is the distribution of shear stress for the I section. Then for the T section, same case here at the flange portion is less, and it's suddenly it is increases, and it is maximum at the neutral axis, and again it is gradually reduces at the end. Shear force is 0 at the extreme edges, and it is maximum at the neutral axis, and it is a shear stress is the parabolic distribution. Okay, that is the you should know how to draw the shear stress distribution for the three sides, the rectangular section, I section, and the T section. This is about the bending stress, simple theory of simple bending. We have discussed about the different types of problems, as well as the what are the how the shear stress distribution in the different types of the cross sections. Okay, thank you.